In section 3.3, we talked about dot products. So dot products, remember those are scalars. Those are just real numbers. In 13.4, we're going to talk about cross products. So when you cross two vectors, its product is going to be another vector. So it's not a number, it's not a scalar, it's actually a vector. What we commonly use cross products for is to determine what we call torque. So torque is a twisting force. And we'll look at why we use cross products to describe torque. Well, first of all, if you have two vectors, u and v, and these are not zero vectors, then their cross product, which we use looks like a multiplication symbol, but it's our cross symbol. So u cross v, that's going to be a vector. And to compute its magnitude, so the magnitude of u cross v is equal to the magnitude of u times the magnitude of v times sine of theta. And here theta is between 0 and pi. It's the angle between u and v. So this vector is going to have a direction. And if you have taken physics, you've probably seen the right-hand rule. The right-hand rule is used to determine the direction of a vector when you cross two vectors. So you use your right hand, and if we look at this diagram here, it might be easier to see. So let's start out with looking at our vector v and looking at our vector u. So here we have vector v, and here we have our vector u. We're going to look at the cross product of u with v, and since u is first in our cross product, what that means is, think about the fingers of your hand if they were sticking out, pointing in the direction of u. And then curl your fingers so that they move towards our vector v. When you do that with your right hand, you will produce a vector that's pointing in the direction of your thumb. And that would be the direction of u cross v. So when you cross two vectors, two non-zero vectors, usually, not always, there's a special case, usually you get a vector that is going to be orthogonal, perpendicular, normal, whatever you want to call it. It's going to be orthogonal to both vector u and to vector v. So here notice that these are right angles that we have. The direction that you cross vectors matters. If we were to look at v cross u, well, it would be very difficult to curl v into u. So you actually have to flip your hand the other way to bring u or v into u. However, if you know the direction of u cross v and you change the direction of the cross product, that just means you're going to change the direction of the vector. So v cross u would be pointing down. Notice though that if you change the direction of your cross, you still get a vector that is orthogonal to both u and v, which is why it's important to determine the direction. In application problems, it does make a big difference whether your vector is pointing up or pointing down. Okay. So moving on, the special case where you don't get an orthogonal vector to both u and v is if the cross product is 0. And that only happens if u and v are parallel. Okay? So again, please note that the order of your cross products does matter. If you change the order, you change the direction. In example 1, what we're going to do is we're just going to sketch some vectors, and we're going to see if we can determine which way u cross v is pointing, which way v cross u is pointing. So I have my vectors u and v. I'm going to go ahead and draw my coordinate system. Remember, this is just a sketch so we can kind of get an idea of the direction that our vector is pointing in. So we have our x, our y, and our z. Our vector u is 2 on the x, 3 in the y direction, and we have our vector u. Our vector v, 0 in the x, 2 in the y direction, 0 in the z direction. So here's my vector v. When I look at u cross v, I'm bringing the vector u into the vector v, and then that would give me a vector that's pointing upwards. So u cross v points up. Another way to say that is that it's in the positive z direction. Okay. So now if we were going to change the order v cross u, what would happen is it'll now be pointing down, or it'll be in the negative z direction. And the next thing we want to do is we want to look at some properties. In this first box, we're going to discuss the geometry of cross products. So this is similar to when we looked at the picture of the addition and subtraction of vectors. First of all, we're going to make sure that our vectors u and v are not zero vectors. We have two cases. Either u and v are parallel, so that means the angle between them is 0 or pi. And in that case, when we cross them, we're going to get the zero vector. So the zero vector has no direction. So the second case is if u and v are two sides of a parallelogram. And that's going back to when we were looking at vector addition. So let's say we have our vector u, we have our vector v, and if we add these vectors together, we will have this vector u plus v between them, and then that would give us the remaining sides of our parallelogram. So in the event u and v are two sides of a parallelogram, then when we compute the area of the parallelogram, it's going to be the magnitude of the cross products. So remember, the area of a parallelogram is its base times its height. So let's go ahead and look at, let me erase this line here. Let's look at the height on this parallelogram. So this red line here represents the height. So I'm just going to call this h. And then I'm going to verify that the area of a parallelogram is the magnitude of u times the magnitude of v times sine of theta, which is simply the magnitude of the cross product. Well, what we have here is we have a right triangle, and we have an angle theta. So if I were going to describe the height, I could use the trig identity. The sine of theta is equal to the opposite side of our triangle, which is our h, over the length of the hypotenuse. The length of the hypotenuse is the length of my vector v, which is simply its magnitude. So now if we take this equation and we solve for h, we have that the height is equal to the magnitude of our vector v times sine theta, and that gives me my formula for the area of a parallelogram, or simply the magnitude of the cross products. We'll do an example in just a minute, but let's look at some more properties. We already talked about the direction of the cross making a difference in the direction of our vector. So u cross v is going to be equal to negative v cross u. So change the direction, it becomes negative. So take a negative, and you're back where you started from. Whenever you are crossing vectors, and your vector is multiplied by some constant a or a constant b, we are allowed to pull those constants out before we do our cross product, and that would be simply a times b on the outside and cross your vectors. So that's an option. If you had a vector and you were crossing it with the addition of two vectors, you can distribute the cross to the two vectors and then add them at the end. Another property we have is that if you're adding two vectors and then you're going to cross that with another vector, then you can distribute that third vector. So you can again do the cross first, and then add. Let's look at our unit vectors. So if you cross ij, that's going to be equal to negative ji. And remember, when we cross two vectors, we get a vector that is orthogonal, perpendicular, normal, whatever you want to use. Typically, perpendicular is used when we're in two-dimensional space. Orthogonal and normal are used when we're in higher dimensions, like three-dimensional space. So if you take I and j and you cross them, you're going to get your third vector k. If you cross k and I, you get j. And if you cross jk, you get I. Now, anytime you cross a vector with itself, you're going to get 0. And that should be the 0 vector, not the number 0. Sorry, that wasn't bolded. Maybe I'll just make it bolded. We'll pretend like that's the 0 vector. Now, we talked about the magnitude of cross products. The question is, how do you compute a cross product? We normally compute cross products with vectors in three-dimensional space. So here we have our vector u written in terms of ijk, and our vector v written in terms of ijk. So the coefficient on ijk for u is u sub 1, u sub 2, u sub 3, and then the coefficient on our vector v for ijk is v sub 1, v sub 2, v sub 3. So if you've had linear algebra, or you use these formulas in other classes, like your physics class, then this should be familiar to you. But if you haven't, when we compute the cross product, remember these are written in terms of I, j, k. So what we're going to do is, our first row is going to remind us that the components are I, j, k. And the order that you're crossing is the order that you make your rows. If u is first in your cross product, then the components of u are first. If v is second in the cross product, then v is listed second when you compute the cross product. Now the question is, what's all the rest of this stuff? Well, whenever we do cross products, what we're doing is we're figuring out what we call a determinant. If you're familiar with linear algebra and determinants, we're going to look at the determinant of what we call a 2 by 2 matrix. So it looks something like this A, B, C, D. When we compute the determinant, we write it with those absolute value bars that you see in the formula above. It's just a cross product, where you're going to cross multiply AB, and then you're going to subtract the product of CB. So that's what we have here. And that's what we're going to do inside these absolute values when we compute our cross product. So what we're actually trying to figure out is the coefficient on ijk for our cross product vector. And we always alternate when we figure out these components. So it's going to go plus, minus, plus. And if this were a higher dimension, then it would go minus, and then plus, and then minus, and plus. And that's how you do this. So we're just going to compute these cross products. Now when we compute these cross products, how do we know what u and v values to put in? Well, it's simple. To compute the coefficient on I, what we need to do is ignore the I. So get rid of that column. Notice that what remains is u sub 2, u sub 3, v sub 2, and v sub 3. And that's what's in our first cross product. So when we compute the second component, we do the same thing. To figure out the component or the coefficient on our j vector, we simply block out the j column, and what remains is going to be our u sub 1, u sub 3, v sub 1, v sub 3. Similarly, if we block out our k column, then what's left over is going to be u sub 1, u sub 2, v sub 1, v sub 2. So that's how you figure out these cross products. Just block out a column. Let's do some examples, but first, keep in mind that whenever we do cross and we get a vector normal or orthogonal to our vectors u and v, any other vector that is normal or orthogonal to u and v will be parallel to the cross. Okay, so these are all going to be parallel vectors. Let's compute 4 times j cross negative 2 times I. And I'm not going to use that big formula, and the reason why is because I can use those properties. I know that this is equal to, I can pull out the 4, I can pull out the negative 2, and then just take j cross I. So I actually don't have to compute. What would 4j be? That would be 0, 4, 0. And then negative 2i would be negative 2, 0, 0 if I was writing it in terms of its components. So I could do that, then I could do the cross product. However, since I already know that this is 4j cross negative 2i, I can use the earlier properties. I could factor out the scalar to get negative 8, and when I cross j cross I, well, I cross j is positive k, so j cross I must be negative k. So this is simply 8 times the vector k. All right. Well, let's verify this. Let's actually compute the cross. So this first vector would be, if you're looking at that formula, that would be your u, and this would be your v. If I was going to compute this cross product by hand, I could do I, j, k. And if I'm doing u first, it would be 0, 4, 0. V would be negative 2, 0, 0. So here's my cross. That's going to be equal to a plus. Figure out the cross product for, if we cover I, we have 4, 0, 0, 0. That would be our I. So it's plus, minus. Cover the j, and you have 0, 0, negative 2, 0. That would be your j. Plus, cover the k, and we have 0, 4, negative 2, 0. That would be the coefficient for our k vector. So let's see if we just get 8k. When I do my cross product, I'm going to multiply. 4 times 0 is 0. So this becomes 0 minus 0 times 0 is 0. And that would be my I. Minus, when I multiply, I get 0 times 0 is 0, minus negative 2 times 0 is 0. And that would be the coefficient on my j. Next one, when I multiply, 0 times 0 is 0, minus negative 2 times 4 is a negative 8, so this turns into a plus 8. That would be my coefficient on k. So you see that 0i, 0j, so all I have is an 8k, which means you could use either form. All right, let's do some more examples. We're going to go back to the area of a parallelogram. In example 3, we're supposed to find the area of a parallelogram, and we have the adjacent sides as being our u, 3i, negative j, and our v is j plus 2k. The area of my parallelogram is going to be equal to the magnitude of u cross v. And here we could look at maybe I'll write it across here. We'll look at our I, j, k, with u being 3, negative 1, 0, and v is 0, 1, 2. Oh, I'm hearing roosters again. Oh, drive me nuts. So that would be equal to, if I cover up my I column, I have negative 1, 0, 1, 2, coefficient on my vector I, minus, cover up the j, I get 3, 0, 0, 2, coefficient on my j, plus, cover up my k, I have 3, negative 1, 0, 1, coefficient on my k, which will be equal to negative 2 minus 0 gives me a negative 2i. 6 minus 0 gives me a positive 6, but this is a minus 6. J. And then the last one would be 3 minus 0, or 3. So it's a plus 3k. So I have my cross product, but I need to figure out the magnitude of this cross product. So really what I'm looking at is figuring out the cross product and then taking the magnitude, right? So I need to take the magnitude of this vector. And the magnitude of this vector is going to be the square root of 4 plus 36 plus 9, which would be the square root of 49, or 7. So the area of my parallelogram is 7 units squared, whatever the units may be. Let's use cross products again. Oh, roosters are awful. Let's use the cross products again. In example 4, we want to find a normal vector to these vectors 0, 1, 2 and negative 3, 1, 4. I can look at this first vector as my u and the second vector as my v. So if I want to find a normal vector to these two vectors, all I have to do is cross them. And it doesn't matter which order I choose. I can do u cross v. That will give me a normal vector. Or I can use v cross u. That would give me another normal vector to these two vectors. So I'll just do the first one, the u cross v. And then we're also supposed to verify results. So we'll talk about that in just a little bit. U cross v is going to be I, j, k vectors, right? Where u is 0, 1, 2, v is negative 3, 1, 4. So the cross product is going to be equal to cover I, and we have 1, 2, 1, 4. This is the coefficient on my I, minus cover j, and we have 0, 2, negative 3, 4, j, plus cover k, and I have 0, 1, negative 3, 1 coefficient on my k. So this is going to give me 4 minus 2 is 2. So this would give me a 2i minus, so this is going to be 0 minus a negative 6, which would be a 0 plus 6. So the determinant is 6, but I have this minus, so it's going to be minus 6j plus 0 minus 3, minus a negative 3 would be a positive 3. So plus 3k. This would be a vector that is normal to the given vectors. To verify, what we're going to do is we're going to look at dot products. So this would be the easiest way to verify if vectors are normal. So remember, if you dot two vectors and your dot product is 0, then the vectors are orthogonal, normal, perpendicular, whatever you want to use. So I have to verify that this vector that I found, 2, negative 6, and here remember you can write this in the vector notation of 2, comma, negative 6, 3. So I want to take this vector and I want to dot it with the two vectors to see if I get 0. So I'm going to first dot this with the vector 0, 1, 2. When I dot that, I get 0 plus negative 6 plus positive 6. So since the dot product is equal to 0, that means those two vectors are normal. And I also have to check to see that 2, -6, 3 is normal to -3, 1, 4. Dotting these two vectors, I get a -6 plus -6 plus +12. So I get 0. So that checks out. Now, if I did use the other order, v cross u, and you can do this on your own if you wish, you'll find that when you get your vector, it will simply be the negative of the vector that we got. So the other vector that would be normal using cross products would be -2, +6, -3. And you can verify to see if you dot them with the two given vectors that their dot is 0. Now these are not the only normal vectors to the given vectors, but this is just a way, cross products are a way to find a normal vector to your given vectors. There's actually infinitely many vectors that are normal to both u and v. So moving on to a common application, and we talked about this in the beginning. When you think about that right-hand rule, you're bringing your fingers in, you're curling them in, you're twisting them. So it seems logical that this cross product could describe a twisting motion or torque. In example 5, it says, suppose you applied a force of 35 newtons to a 0.2 meter wrench. This wrench is attached to a bolt in a direction perpendicular to the bolt. So the wrench is perpendicular to the bolt. Determine the magnitude of the torque when the force is applied at a 65-degree angle to the wrench. So a lot of words going on here. What does it all mean? Okay, well, first of all, we're supposed to determine the magnitude of the torque. So I need to assign a variable to torque. In physics, it's common to use the Greek letter tau for torque. Sometimes this is also used for torsion, which is a little bit different. So I'm going to let this Greek tau be my torque vector. So that would be this vector here. Okay, so I have my torque vector. And now I'm going to apply a force. Typically we use capital F when we're going to talk about force. So if you look down at the handle of your wrench, because that's where you're going to be applying your force, we're going to try to move the handle of the wrench in a downward motion. So we're going to have this downward force. So that would be my force vector. And then we have another vector as well, the vector that represents the wrench. Okay, so that would be this green line. And I've assigned R to the vector to represent the wrench. So I have all this information, and I also have additional information. I know that when I do apply the force, it's going to be at a 65-degree angle, so I'm going to move the wrench 65 degrees. Oops, sorry. So I'm going to be moving my wrench 65 degrees down. So that would be this theta here at the handle of my wrench. Okay. Well, oftentimes it's helpful for us to move vectors so they have the same tail. Now remember, and we're looking at this force vector here. Vectors are equal if they have the same length and the same direction. So I can actually look at this vector, and I'll look at here at the bolt. So I can move that force vector so that it has a common tail with my vector r and my torque vector. So they all have the same tail. Now my torque vector can be found by the cross product of the force vector and the vector r that represents the wrench. So I'm going to write down some things I do have. So this torque vector is going to be normal to F and R, and I can find it by crossing F and R, or should it be R and F? Remember, order matters. So if we bring our vector R down to our vector F, then it will give me the correct direction on my torque vector. If we actually bring F into R, imagine curling your fingers around, that will give me a vector that's pointing in the opposite direction, which is not what I want. So the direction that I'm going to be crossing to get my torque vector is R cross F. And it's also the direction that I am moving my wrench, isn't it? Aren't I bringing R into F? So when I cross those two vectors, I get my torque vector. Now we were supposed to determine the magnitude of the torque vector, so we actually want the magnitude. So I could compute the cross of R cross F, which means I would have to know all the components of both vectors. Or I could also use the formula that we had previously, that the magnitude of a cross is going to be equal to the magnitude of R times the magnitude of F times sine of theta, where theta is the angle between them. And the reason why I should probably use that one is because of the information that I actually have. If we look at the angle between F and R, and we look at this angle theta, this is 65 degrees. So I have theta. But do I have the magnitude of R and the magnitude of F? Well, let's look at our given information. It says, suppose you applied a force, and here the force is 35 newtons. Okay? That's the magnitude of F. So I know that the magnitude of F, is the 35 newtons. So we're applying this force to a 0.2 meter wrench. So that is the length of R. So this 0.2 meters, that is the length of R, or the magnitude of R. So I actually have everything. The magnitude of R is simply 0.2 meters, and the magnitude of F is 35 newtons, and then I'm going to multiply that by sine of 65 degrees. So you would put this in a calculator. Remember that your mode needs to be in degrees. When I put it in my calculator, I got approximately 6.4, and these are Newton meters. So remember that that's actually joules. So this is 6.4 J for joules, and joules is work. So that's the amount of work we're doing when we describe torque. Okay. So let's look at another problem. Oftentimes we use cross products when describing particles, charged particles moving in a magnetic field. So let's discuss what all of this means. We're going to be looking at magnetic force. Okay? So we're looking at a moving electric charge. So it's either going to be isolated like some electron, or it's going to be some current flowing through a wire. Okay? So this electric charge has a velocity v. When it enters a magnetic field, we'll call the magnetic field B. Okay? So it's going to experience some sort of force. So if the charge is Q, then to compute the force vector, it's going to be the equation Q times V cross B. So the magnitude of our force is going to be, now this is not really the magnitude of Q. Q is just a scalar. It's a real number. It's a measurement. So this is actually the absolute value of Q times the magnitude of V times the magnitude of B times sine of theta, and theta is the angle between V and B. So this is similar to what all of that describes. So if you look at this curve, you can imagine this, say it's an isolated charge, it's some particle, and it's moving along, and then all of a sudden, bang, it encounters a magnetic field. So let's just say that we call this magnetic field, which would be a force on our particle. We're going to call that B. At the instant that this particle hits that magnetic field, we can describe its velocity using this vector V. So here we have the angle theta between the two. If we cross those vectors, and then we multiply it by the absolute value of the charge, it's just some constant, it's a scalar, what we're going to get is we're going to get this force vector. So something that we do have to note, that if V and B are parallel, so imagine this particle entering in a magnetic field and it's actually going in the same direction or in the opposite direction of the magnetic field. Okay. Then the force is 0. So if V is parallel, so the two double lines, if V and B are parallel, so if V is parallel to B, then our force vector is going to be equal to the 0 vector. So that's the idea, and that's where we could use cross products. In example 6, we're going to apply this idea. So let's say we have a particle with a positive unit charge, and it's going to enter a constant magnetic field B, and B is given as I plus J, with the velocity of 20k. We want to find the magnitude and direction of the force on the particle. All right, so I want to find the magnitude and the direction of the force. So our force vector, going back to what we looked at before, is going to be equal to Q times V cross B. But we're trying to find the magnitude, right? So actually what we're looking at finding is the magnitude. And that would just be our absolute value of Q times the magnitude of V times the magnitude of B times sine of theta. All right. So I can either compute that force vector using that first formula and then find its magnitude, or I can simply use this second equation. Well, first of all, what is Q? So let's look back at our problem. It says a particle, Q is our charge, right? So this particle has a positive unit charge. So when we say unit, unit is 1. So we have positive 1 charge. that tells me that Q is equal to 1. So I know what Q is. What about V and B? Well, we're entering a magnetic field B, which is equal to IJ. And that tells me that my vector B is, and I'm going to use vector notation, so it's going to be 1, 1, 0. All right, so I found B, and I know my velocity vector is 20k. So if I were to write that using vector notation, V is going to be equal to 0, 0, 20, 0i, 0j, 20 on the k. Okay, so I could compute my force vector. I think I'm going to try that by computing the cross product. Now I don't need to look at this Q because remember that was 1. So this is gone. I could easily compute the magnitude of V, the magnitude of B, and I could use that second equation. I don't have theta, but I could find theta. But let's say I don't feel like figuring out what theta is. Then I would use the first equation, find my force vector, and then take its magnitude. So I'm going to try that method first. So the cross of V cross B, remember we're looking at I, J, K. I have to put in V first, so that's going to be 0, 0, 20, and then B is 1, 1, 0. This is going to be equal to cover I, J is 0, 20, 1, 0. Coefficient on I minus K is covering, or J is covering J, I get 0, 20, 1, 0. Well, same thing. And that would be my J plus K, cover K, and you get 0, 0, 1, 1. And that's your K coefficient. So 0 minus 20 would be equal to a negative 20I. 0 minus 20, so that would be a minus 20 or a plus 20J. And then K is going to be 0 minus 0, so plus 0K, which is gone. If I were to write this in vector notation, it would be the vector negative 20, 20, 0. To compute its magnitude, because that's what I need the magnitude of the force. It would be the square root of negative 20 squared, so 400 plus positive 20 squared, and then the 0, square root of 800. If I wasn't putting this in a calculator, that would be 400 times 2, so 20 square root of 2. And then if I were just plugging this in a calculator, I'm going to go in decimal place. So I'm going to write this as 28.3. What are the units? So force is newtons, or the magnitude of force is newtons, right? So this is newtons. Okay, well, let's say that I wanted to use the second equation. How do I find theta? Sometimes it's not this easy. But I conveniently chose values that were nice. So remember, we're in three-dimensional space. Let's draw ourselves a little sketch here. When we look at B, it's going to be 1, 1, 0. So 1, 1, 0 will probably be, let me use a different color. So let's go green for B. It's going to be a vector in the xy plane because its z component is 0. But now when we look at vector v, and I'll use red for that, it's got 0 for x, 0 for y, but it's got a 20 for its z component. Okay? And this would be our v. Oh, that's a terrible arrow. So B is in the xy plane, V is going up in the z direction, which means these guys are actually orthogonal. So the theta is going to be equal to 90 degrees. Looking at our second equation, the magnitude of f, well, the absolute value of q is just 1. So we have the magnitude of v times the magnitude of b times sine of theta. The magnitude of v is the square root of 20 squared, which is 20. The magnitude of b is the square root of 1 plus 1, which is the square root of 2. And sine of theta is sine of 90 degrees, which is simply 1. Notice that I got the exact same answer as I did when I computed the cross and then I took its magnitude. However, we're not done. The second part of this question said to not only find the magnitude, but the direction of this force vector. All right. So let's look at this being our magnitude. And now let's look at our force vector. To do that, I think I'm going to just sketch a diagram. My force vector is the vector negative 20, 20, 0. Okay? Since the z component is 0, and here, whoops. Since the z component is 0, I'm just going to sketch this vector in the xy plane because z is 0, right? So if I just go negative 20 on the x and a positive 20 on the y, I get my vector. I'm going to use a different color here. This would be my force vector. So one way to describe it is to first figure out what this angle is. Well, it's going to be 90 plus 45, so it's 135 degrees. So one way I could describe it is the direction is 135 degrees in the xy plane. Notice that I don't really need to describe it in terms of a z-coordinate because the z-coordinate is 0. Let's look at one last example, and hopefully the roosters will stop crowing. Now this example mathematically is actually not very hard to figure out. The problem is, what does all of this mean? Where is what? When you look at example 7, it says an electron, and then in parentheses it has Q equals to 1.6 times 10 to the negative 19 C, enters a constant 2T magnetic field at an angle of 45 degrees to the field with a speed of 2 times 10 to the 5 meters per second. Find the magnitude of the force on the electron. Okay, so this is an electron, and it has a charge of Q. It's going to enter a magnetic field. So we're going to let V represent this, the velocity of this electron when it enters its magnetic field. And I'm going to use B for the magnetic field. we're supposed to find the magnitude of the force on the electron. So we're supposed to find the magnitude of the force. That's what we need to find, right? Okay. Well, I have V and B. I have Q. First of all, I don't know if you know what these measurements are. C is coulombs, and T is typically what we use when we describe units in a magnetic field, so those are Teslas. Okay. Well, I do have some formulas. I have that the magnitude of my force vector is equal to the absolute value of Q, and I do have Q, times the magnitude of V, whatever that is, times the magnitude of B, whatever that is, times sine of theta. And it looks like since it's entering the magnetic field at an angle of 45 degrees, it looks like that's going to be my theta. So since I'm finding the magnitude of the force, I know my units are going to be in newtons. So I know Q. Let's see, what is the magnitude of my electron? Well, remember, velocity is direction and speed. So if we look at this, it says it enters the magnetic field at a 45-degree angle with a speed of 2 times 10 to the 5 meters per second. So that's my magnitude. It's 2 times 10 to the 5. I'm going to leave off the units because I already know that the magnitude of my force is going to be in newtons. Okay, because force is in newtons. Let's see. So I have Q. I have magnitude of V. What about B? Well, it says that it enters a 2 Tesla magnetic field. This 2T, that's not a vector. That's a measurement. So that is the magnitude of B. Again, I'm going to leave off the T, and then I can write the magnitude of my force as being the absolute value of Q, which is 1.6 times 10 to the negative 19, times the magnitude of V, which is 2 times 10 to the 5, times the magnitude of B, times sine of 45 degrees. So again, this is not a very difficult question. The only reason why I have it here is because there might be some confusion on what everything means and how do you find it. All right, so this is just a matter of plugging this in your calculator. I'm going to go to, so if I was going to write this with 1 decimal place, it would be about 4.5 times 10 to the negative 14. And then that would be newtons. So this is the magnitude of the force. And that's it for this section.